Welcome back to the existence and uniqueness theorem of initial value problems. In the last lecture we have seen that an initial value problem has a unique solution if the function satisfies a Lipschitz continuity condition with respect to the dependent variable y. So, we deal with initial value problem. So, our initial value problem dy by dx is equal to f of x y, and the initial condition is y at x 0 is y 0. So, where f is a function which is defined on a domain which is a subset of R2 to R, and x 0 y 0 is a point, an interior point inside D, is D, and is x 0. This is point y 0. So, x 0 y 0 is the initial point, initial condition, and we now prove the existence of solution and uniqueness of solution under Lipschitz condition with respect to y and a continuity condition with respect to x. So, Picard's theorem gives both existence and uniqueness, and uniqueness part we have already proved, and in this theorem I will concentrate only on the existence part. So, let me state the Picard's theorem. Let D be a domain in R2 and f from D to R be a real valued function, a real function satisfying the following conditions, satisfying the following conditions. First one is f is continuous, f is continuous on D with respect to both the argument, that is meaning of the all domain D, and f of x y is Lipschitz continuous with respect to y on D with the constant, with the Lipschitz constant alpha, which is a constant, positive constant, and let x0 y0 be an interior point on D, and let A and B be constants such that the rectangle R defined by set of all x y such that x minus x 0 is less than or equal to A and y minus y 0 is less than or equal to B. This rectangle is inside the domain D, and let M be a constant, capital M be a constant defined by maximum of the function f x y, where x y is in D. This maximum exists because f is continuous. So, and we take x y to vary in the rectangle R. Rectangle is a closed set inside D. So, therefore, this maximum exists, and let us define another constant h is equal to minimum of A and B by M. Then the initial value problem has a unique solution y on the interval x minus x 0 is less than or equal to h. So, this is a Picard's existence and uniqueness theorem. It gives both existence and uniqueness. The conditions we assume is f is continuous on D and f x y is Lipschitz with respect to y on D with the Lipschitz constant alpha, and the initial point x 0 y 0 is an interior point on D, and we take a rectangle which is inside the domain D, with a closed rectangle inside the domain such that two constants are defined. M is the maximum of the value function in the rectangle R, and h is the minimum of A and B by M. So, if I look at, so this is domain D, and inside the domain we define a rectangle So, this point is x 0 y 0. So, it is the point x 0 y 0, and this side is x is equal to x 0 plus a, and this side x is equal to x 0 minus a, and this side is y is equal to y0 plus b, and this side y is equal to y0 minus b. So, we now prove the theorem. Proof. So, the proof has more technical details. So, since R is a closed rectangle, R is a closed rectangle. So, inside the domain D, F satisfies all properties mentioned inside D, inside R. Now, there are two situations. Two situations. One is if A is less than B by M. So, remember our definition of the constant H, which is a minimum of A B by A. So, H is defined as minimum of A B by M. So, in case if A is less than B by M, then H is equal to A, and if in that case we have a full the same rectangle, H is equal to A, and if A is not, if B by M, if B by M is less than A, then H is equal to B by M. In that case, H is a number which is smaller than A. So, in that case we will have another rectangle. So, we will have another rectangle . So, this line is x is equal to x0 minus h. So, this line is x is equal to x0 plus h. So, we have two rectangles, one this you call it R1, and the first rectangle is R, or we can write R is set of all xy such that x minus x0 is less than or equal to A, y minus y0 is less than or equal to B, and R1 is set of all xy, x minus x0 is less than or equal to h, y minus y0, the bound for y is the same, B. So, if A is less than B by M, then these two rectangles coincide. In this case, R1 is same as R. If B by M, if A is greater than B by M, in this case, we will see that R1 comes inside R. So, Picard's existence and uniqueness theorem says that it has a solution, the solution starting from x0 y0 is a solution, and the solution exists in the interval x minus x0, the solution exists in the interval x minus x0 less than or equal to h. So, solution existence solution is on R1. So, depending upon the value of A, if A is less than B by M, then this the solution exists for the larger rectangle. If A is greater than B by M, then the solution exists on a smaller rectangle R1. Okay, so we prove the theorem by the method of successive approximation. We prove the theorem by successive approximation of the Picard's successive approximation of the Picard's iterants denoted by phi 1x, phi 2x, phi 3x, etc. This iterates this because iterants are defined on the interval x minus x 0 less than or equal to h. It's defined on x minus x 0 is less than or equal to h, and are defined by phi 1x. So, phi 1 is equal to y 0 plus integral x 0 to x f of t y 0, which is the initial condition that y 0 dt is a constant function dt, and phi 2x is y 0 plus integral x 0 to x f of t phi 1 t dt, etc., etc., and phi n t. So, phi n of x is y 0 plus integral x 0 to x f of t phi n minus 1 t dt. So, call this as equation 1. So, we prove the existence of solution to the initial value problem on one side of the interval x 0 plus h. We will prove the existence on one side of the point x 0 to x 0 plus h. Similar arguments hold for x 0 minus h to x 0. So, therefore, we prove only on one side, and uniqueness is already been proved. Uniqueness of solution follows from uniqueness theorem. Okay, theorem which we proved in the previous lecture. Now, we divide the proof, we divide the proof into 4 parts. So, part A, part B, part C and part D. So, part A is, in part A we will prove that the functions phi n, the sequence of function phi n defined by equation 1 is well defined, okay, that is and it is also continuous, and call it is A part is well defined, and B is phi n, phi n's have continuous derivatives C, it obeys an estimate phi n x minus y 0, the difference between the initial point and all, and phi n x. This is less than or equal to B, that means all phi n's are within the rectangle B on x 0 plus h, the interval on which we are proving the existence, and D, when we evaluate the function f at this phi n x. So, this is well defined. So, this is part A. In part A we will prove that the Picard's iterants defined by equation 1. So, defined by equation 1, this phi n x, this equation, this is well defined, and phi n's have continuous derivatives on the interval x 0 plus h, and phi n obeys an estimate phi n x minus y 0 is less than or equal to B on this interval, and f of x phi n x is also defined. That is part A, we will prove it. And part B, so part B is the functions phi n x, the sequence of functions we defined by 1, satisfy the following inequality. The following estimate. That is absolute value of phi n x minus phi n minus 1 x is bounded by m by alpha. M is the maximum value of the function, m is the maximum value of the function on the rectangle, and alpha is ellipsis constant times alpha h to the power n divided by n factorial. This happens for all x in the interval x 0 plus h. So, the Picard's iterans defines a sequence of function. That sequence of function satisfies this estimate. Now, part 3, that is a part C, is we will prove that as n goes to infinity, the sequence of functions phi n, this converges uniformly. So, this sequence of functions converges uniformly to a continuous function call it phi, a continuous function phi on the interval x0 plus h. Now, the fourth part D of the proof is that we will prove that the limit function which is obtained in part C phi satisfies the limit function phi satisfies the given initial value problem, IVP on the interval x0 plus h. So, in short, if we prove all these 4 parts, part A, B, C and D, then we obtain a limit function phi which happens to be the solution of the initial value problem, that proves existence of solution to the initial value problem, and uniqueness is already been proved in the uniqueness theorem. So, let us prove part by part. So, proof of part A. So, this we prove this by mathematical induction. Prove this by mathematical induction. That is, we will assume that the result is true for n minus 1, and then we will prove that it is also true for n. Then we will check this is correct for n is equal to 1, and then by the method of mathematical induction we conclude that this is true for all n. So, assume that phi n minus 1 exists. So, phi n minus 1 exists and it has continuous derivatives. On the interval x0 plus h, and it satisfies the estimate, and it satisfies phi n minus 1 x minus y0 is less than or equal to b. Okay, for all x in the interval x0 plus h. Now, after assuming this, we are going to show that these properties are also true for phi n. If we assume that these properties are true for phi n minus 1, we are going to show that this property is true for n phi n. So, this implies so this above conditions implies that x phi n minus 1 x, the point x phi n minus 1 x is in the rectangle R1, because you have this bound phi n minus 1 x minus y 0 is less than or equal to b. So, that shows that it and that x is in the interval x 0 plus h. So, therefore, the point x phi n minus 1 x is in R1. Okay. Now, also if this point is in R1, we have we can evaluate the function, we can evaluate this function at this point. So, f of x phi n minus 1 x is defined, and phi n minus 1 is continuous and f itself is continuous, is defined and is continuous with respect to x on x 0 plus h. So, further we have if we evaluate the function f x phi n minus 1, since that is in the rectangle R1, this can be evaluated for the function f, because f is defined on R1, and this is going to, and we have seen this will have a bound less than or equal to m by hypothesis. So, maximum value of f on R is m, that is the maximum of it. So, this on x 0 plus h, and all this discussion helps us to look into the integral. So, consider the function phi n x, which is defined as y 0 plus integral x 0 to x f of t phi n minus 1 t dt. Okay. Now, we have seen that the function f is, this function f is continuous with respect to x, and it is well defined, and therefore, the properties mentioned above helps us to conclude that so phi n x exists. So, y 0 plus integral x 0 to x, and for the continuous function f, this integral exists and has continuous derivative. Since f is continuous with respect to the second argument, okay, f is continuous with respect to the second argument. So, therefore, this integral exists, and that can be differentiated to get a continuous derivative on the interval x 0 plus h. Now, also consider, so also if you find the estimate phi n x minus y 0 the absolute value of phi n x minus y 0 by definition. This is absolute value of integral x 0 to x f of t phi n t dt, and this is less than or equal to integral x 0 to x absolute value of phi t phi n minus 1 phi n minus 1 above phi n minus 1 t dt, and we have seen that f of t phi n minus 1 t is bounded by a constant m. So, therefore, this is less than or equal to integral x 0 to x em dt, which is integral x 0 to x. Okay, can straight away integrate this one and get m into x minus x 0, and x minus x 0 is less than or equal to h. So, this is m of less than or equal to h, and mh is obviously less than or equal to b by definition of h. So, h is minimum of a b by m. So, this all arguments helps us to conclude that x phi n x, this point, this lies in the rectangle. So, x phi n x lies in the rectangle R1, and hence f at f evaluated at x phi n x is defined. Since f is continuous, so f is continuous, phi n is continuous, and this f of x phi n x is continuous, is defined and continuous on the interval x 0 plus h. So, what does it say? It says that all properties, so says that this phi n is also satisfying all the properties we assumed in part A. Now, with the assumption that if phi n minus 1 satisfies the properties, then phi n also satisfies the properties. Now, let us check for the case when n is equal to 1. So, when n is equal to 1 case, so we have phi 1 x, which is equal to by definition y 0 plus integral x 0 to x f of t y 0 dt. So, obviously, phi 1 is well defined. Obviously, phi 1 is defined, and f is continuous, and y 0 is a constant function which is continuous. So, therefore, f is continuous, and therefore, this phi 1 is defined and has continuous derivative. Continuous derivative on x 0 plus h. And also, if you find the estimate, so also the bound phi 1 x minus y 0, by definition this is less than or equal to integral x 0 to x f of t y 0 dt, and f is bounded by m. So, this is less than or equal to m into x minus x 0, which is less than or equal to mh, and which is bounded by is b. So, obviously phi 1 also satisfies these properties. So, therefore, this implies that x phi 1 x is in R 1, and hence f of x phi 1 x is continuous on x 0 plus h. So, therefore, this implies that the properties are true for n is equal to 1. So, what we have proved in part A is the properties of phi n's like they are all defined, and phi n's are having continuous derivatives, and when phi n is put into f, that is also continuous, and phi n x phi n's are in the rectangle. These all properties are true for n is equal to n minus 1, that is what we assumed, and from that we have proved that it is also true for the case n, and it is also true for n is equal to 1. Thus, by the method of mathematical induction, so by the method of mathematical induction, phi n, so phi n of, that is a sequence of induction, phi n sequence of functions defined in 1 by the Picard's iterants that possesses all desired properties in the interval x 0 plus h. So, hence part A. So, part A of the proof is established by mathematical induction. Now, we look into part B, proof of part B. Part B, what we are looking for? We are looking for an estimate for the Picard's iterants. So, we again we prove this again by mathematical induction. We prove this also by mathematical induction. induction. So, assume that is true for n minus 1. Assume that the estimate is true for n minus 1. That absolute value of phi n minus 1 x minus phi n minus 2 x is less than or equal to m alpha to the power n minus 2 divided by n minus 1 factorial into x minus x 0 to the power n minus 1. For x in the interval x 0, x 0, x 0 plus h. We assume that the estimate is true. This inequality is true for n minus 2. So, call this inequality as 2. Now, by using this inequality, we find the estimate for phi n. So, then phi n x minus phi n minus 1 x, this by definition of the iterants is integral x 0 to x f of t phi n minus 1 t minus f of t phi n minus 2 t dt. So, by definition of the definition of the functions phi n. Good. Now, by part A, so what do we have in part A? We have that phi n t phi n x minus, in part A we have shown that phi n x minus y 0 phi n x minus y 0. This is less than or equal to b for all n and x in the interval x 0 plus h, which we have established in part A. So, hence what we have is the point x phi n minus 1 x and x phi n minus 2 x, these two both the points are in R, okay, are in the rectangle R1. Okay, for x, of course, in the interval x 0 plus h. Since they are in R1, f satisfies all the nice properties in R1, including the Lipschitz condition continuity properties. So, therefore, by Lipschitz continuity, of f. So, if we apply the Lipschitz continuity of f, we have, so on this on this difference, if we apply Lipschitz continuity over here, we have, so absolute value of phi n x minus phi n minus 1 x, which is less than or equal to alpha times, alpha is a Lipschitz constant, integral x 0 to x phi n minus 1 t minus phi n minus 2 t dt. So, here obviously this is less than or equal to integral x0 to x f of t phi n minus 1 t minus f t phi n minus 2 t dt, and applying the Lipschitz continuity, and the Lipschitz constant is alpha. So, therefore, alpha will come out is alpha times integral x0 to x1 phi n minus 1 t minus phi n minus 2 t. Now, by the assumption, so therefore, what is our left hand side? Our left hand side is phi n x minus phi n minus 1 x is less than or equal to, what we have is alpha times x0 to x absolute value of phi n minus 1 t minus phi n minus 2 t dt. Now, by using our assumption, okay, by 2 is our assumption. So, we assume this is our 2. We assume that for n minus 1 case, this we have. If we assume this, then we get this, this is alpha times integral x0 to x. So, putting the values m of alpha n minus 2 by n minus 1 factorial and t minus x0 to the power n minus 1 dt. If we integrate it, so with respect to t, so this is less than or equal to, you get m into alpha, you can take outside alpha to the power n minus 1 by n minus 1 factorial, then integrating t minus x0, we get t minus x0 to the power n by n, and you have to evaluate it at the point x0 and x. So, this gives you that when x is equal to, when t is equal to x0, this vanishes, and t is equal to x, you get x minus x0. So, this is m into alpha to the power n minus 1 by n factorial, n minus 1 into n factorial into x minus x0 to the power n. So, which with just an adjustment of constants, if I divide by alpha, m by alpha into alpha to the power n by n factorial into x minus x0 is always less than or equal to h. So, this is h to the power n. So, therefore, this is less than or equal to m by alpha into alpha h to the power n by n factorial. So, as x minus x0 is less than or equal to h. So, therefore, this implies that the inequality is true for n. We assume that the inequality is true for n minus 1, then we could prove that the inequality is true for n. Now, for the case, so let n is equal to 1, check for the case n is equal to 1. When n is equal to 1, we have that phi 1x minus y0 is equal to integral less than or equal to integral x0 to x f of t y0 dt t y0 dt, and f of t y0 is less than or equal to m. So, therefore, this is less than or equal to m into x minus x0, which is again less than or equal to m of h. So, it's true for the case alpha is equal, so n is equal to 1. So, therefore, it's true. So, for alpha is equal to 1 case, it is true. So, therefore, by mathematical induction, the inequality is true for all n. So, therefore, this proves part B. So, as we have seen, the total proof of the Picard's existence and uniqueness theorem is divided into 4 parts. Part A gives some nice properties of the sequence phi n, and part B gives a very useful estimate for the sequence of functions phi n, and both these parts are proved. Now, part C and D. In part C, we will prove that the sequence phi n that converges uniformly to a continuous function, and part D we will prove that limit function is a solution to the initial value problem. So, these 2 parts we will prove in the next theorem, next lecture. So, let us just recall. Part A gives nice properties on the sequence of functions phi n, which are the Picard's iterates. Now, part B gives a good estimate for the Picard's iterates phi n. Now, remaining part we will prove in the next theorem. Okay. Bye.